Today we have to find out the relation between current and drift velocity. In previous class we have learnt the relation between drift velocity and relaxation time. First of all, we have to know that a metallic conductor consists of a huge number of free electrons. When metallic conductor is applied to the electric potential, then electric field is set up, and hence the free electron moves from minus terminal to plus terminal and current flows in opposite direction. This is the main logic in this case. So we have to write down some points. So a metallic conductor consists of huge number of free electrons. So metallic conductor consists of a huge number of free electrons. This is PQ. Let PQ is a metallic conductor having length L and cross-sectional area, that is A, that is length L and cross-section area, that is A. Current is flowing in the direction and electron flows in this direction. So this is the direction of current and this is the direction of electrons. So, and the conductor is applied potential difference between two ends of it, that is two ends of it. The electrons are drifted to in this direction, positive terminal from negative terminal, that is negative terminal of the source, drifted towards in the direction. The current I flows from plus positive terminal to negative terminal, shown in diagram. So current flows from in the direction positive to negative as shown in diagram. So let two sections, that is AB and CD of the conductor. So let two sections, that is AB and CD of this conductor, two sections. This is AB. Now electrons, so we have to find out the number of electrons in this region. So let n be the number of electrons, n be the number of electrons per unit, number of electrons per unit volume of the conductor, per unit volume of the conductor. So, and let Vd, that is Vd is the drip velocity of the free electrons. Vd is the drip velocity of the free electrons. So we can calculate, that is the number of electrons. So number of electrons, so that is the number of electrons. So number of electrons crossing CD sections, number of electrons crossing CD sections in time dt, from AB section, that is we can write, so n equal to that is n into A, that is volume, so into Vd into dt. So show the charge, so charge that is dq, crossing in dt second, that is dq equal to we can write, we multiply in this E, so n E A Vd into dt, because this is the number of electrons, one electron has charge E, so net charge, that is into E. So from this equation we can write, that is n E A Vd, this is I, so n E A Vd. This is very important relationship, and we can also get, that is Vd equal to I by NEA. This is equation number 2. So from this equation we can get, that is I proportional Vd, since NEA constant, taking constant, so the current flowing through the conductor is directly proportional to the drip velocity of the free electrons. So we have learned that is equation of I, and from this equation we have calculated that is Vd equal to I by NA. So Vd depends on that is I and depends on area. If now we have to know what is mobility. Mobility is defined as that is mu equal to that is Vd divided by E. This is the relation of mobility. Here mu is mobility of free electrons. Mu is mobilities of free electrons. So if E equal to 1, then we can get that is mu equal to Vd. So mobility is equal to Vd when E is 1. So it is defined as the drip velocity. It is defined as the drip velocity. It is defined as the drip velocity of free electrons. It is defined as the drip velocity of free electrons due to the applied electric field of strength, unity. This is the electric field of unit strength or strength unity. So this is the definition of Vd. So from this equation we get that is Vd equal to mu into E. This is a relation. Again I know that is I equal to NEA into Vd. Putting this value Vd, so I equal to NEA that is mu into E. So here we conclude that is E proportional mu, and also we conclude so I proportional mu and I proportional that is E. Here we conclude when NE a constant, and then we can conclude this lesson, and when this part is constant, NE a mu constant, then I proportional that is E. So this is the relation. Now we know that is E equal to V by L. So I equal to we get that is mu a NEA V by L, NEA V by L into mu. So we can write NEA mu that is V by L. This is the relation of mobility with current. So electric current, the electric current is directly proportional to the mobility of free electrons. So with the help of Vd drip velocity, we can easily calculate different types of numericals. Here that is I is given, I that is 15 ampere, and A is given, that is 10 to the power minus 5 meter square. N is given, that is 8.4 into 10 to the power 28 meter to the power minus 3. So E 1.6 into 10 to the power minus 19 coulomb. So Vd equal to I by NEA. So I, that is 15, N, that is 8.4 into 10 to the power 28, that is E, that is 1.6 into 10 to the power minus 19, and A, that is 10 to the power minus 5. So we can get the value easily by calculating 1.116 into 10 to the power minus 4. Hence drip velocity of free electrons is 1.116 into 10 to the power minus 4 meter per second. So next numerical, that is A is given 10 to the power minus 4 and I is given 2.4 ampere and N is given 5 into 10 to the power 28. So with the help of this relation, that is Vd equal to I by NEA. So putting the value of I, that is 2.4, N E 1.6 into 10 to the power minus 19 and E, that is 10 to the power minus 4. This is the unit of meter square. So Vd equal to, we get the value, that is 3. By calculating all these things, we get the value, that is 3 into 10 to the power minus 5, that is meter per second. So drip velocity is there. So with the help of this relation, we can easily calculate the different types of numericals. So this relation between the current and drip velocity is very important. It is useful for different examination purpose. I think all students watch all my videos, and these videos are very helpful for different types of examinations. Thank you all my dear students. Thank you all my dear friends.